in this case, as I pointed out before, a logarithm base e gets its own special place, okay? And that is, symbol is just ln, okay? And that stands for natural logarithm. And I can give you hints later in the week on why e gets its own special symbol, but
because it's God's favorite number.
Because it's God's favorite number. Whether you believe in God, nature, the natural order of things, the Big Bang had no intelligence behind it. I respect all those beliefs, but whatever. So he seems to be God or the universe's favorite number, in my humble opinion. So it gets its own special logarithm notation. The full explanation and proof of why that's the case, I don't think you get really well until you get to calculus. Okay, so these are the two exceptions to this notation. If you don't see a number there, the base is 10. If you see ln, the base is e. Now, your calculator, if you take a look at your TI-83, only has two logarithm-related numbers. Okay, buttons on it, and these buttons, what are they, Amy?
Log and ln.
Log and ln. So your calculator will only deal in base 10 and base e.
So how do you get it in the other base?
We're going to learn that in a sec. But first I want to talk about why you need a calculator for this at all, as opposed to a table. Logarithms aren't just for whole numbers, for integers answers. They also apply to, let's take a look at something here. Saul just gave the answer to this one. Saul, what'd you say the log base 10 of 100 is? 2. You're saying 10, which if you don't see any number, you understand to be here, squared equals 100. Tell me something about what you think the log base 10 of 99 would be.
9.9.
Not 9.9, because it's not where you're thinking multiplication again. What do you think, Emma? Nope.
2.
Be close to 2.
1.99.
1.99. Did you find it on there? All right. Solve that on the calculator as 1.99. This is kind of a new idea here, because this rearranged to 10 squared equals 100. This must rearrange to 10 to the 1.99 power. This will be approximate, it's rounded, is 99. We've already talked about fractional exponents. Now, if there are fractional exponents, doesn't it make sense that there would also be decimal exponents? We've already raised things to fractional powers, right? Yeah. Now you got to get to the idea that in addition to fractional exponents, there are decimal exponents as well. In decimal exponents, you can sort of approximate in your head, like if 10 squared is 100, then the log base 10 of 100 is 2. Then the log base 10 of 99, since 99 is a little bit less than 100, the answer 1.99, it makes sense, should be a little bit less than 2. If you know a lot of exponents off the top of your head, if you're one of these people who's pretty quick to know that like 4 cubed is 64, like 5 cubed is 125, then a lot of these answers will make sense. But still, your calculator can only do natural logarithms and logarithms base 10. So we need something else. And I'm going to give you a formula for, and I may prove where it comes from later in the week, but for today I'll just hand it to you. And this is the change of base rule. Change of base rule. Okay? Change of base rule says that, let me make sure I write this correctly. If you have the log base A of the number B, okay, where these can be any numbers you want, this is going to be equal to the log base 10 of b divided by the log base 10 of this base a. Incidentally, it will also be equal to the natural log of b over the natural log of a, or for that matter, you can change it to any other base. It will be, pick any number c and make that your base. And this change of base pattern will hold. How does this work on your calculator? Okay, let's do one you know first. One you should know. I think I just said it. How many times do I raise? What power do I raise 4 to get 64? 3. 4 times 4 times 4. So this answer should be 3. Your calculator doesn't have a log base 4 button. But what I want you to do on your calculator right now is double check this observation by doing the log base 10 of 64 divided by the log base 10 of 4. And tell me what you get. 3. Let's try it again to be sure. Give me the natural log of 64 divided by the natural log of 4. What do you get?
I didn't get that. I got log 64 divided by log 4.
Oh, close your parentheses. Thank you. Try to get with closed parentheses, Saul. Your calculator will give you this parenthesis. Make sure you close this one.
Do you have to do it in one equation?
No, you can do it in two.
I didn't. I got 16. I still got 3.
You got 3? How'd you get 16? Oh, no. You're doing 64 divided, log of 64 divided by 4? No.
Is that what we're supposed to do?
Log 64, close parentheses, divided by log 4.
Now I got 2.9. No, close to 3.
Oh, you're doing the decimals. It's rounding for you. Okay. You'll get it exact if you do it in one string.
I did in one string.
May I see? I'm curious then. Log 16.
I need a bigger calculator.
All right, you did log 16, not 64. Okay, yeah. If you type it in correctly, you'll get 3 every time. So that's change of base. So your calculator now can tell you the logarithm of any number you can imagine, any base you can imagine. A couple other properties of these I want to get to. Logarithms can actually be used to sort of cancel out exponents. Well, what else am I going to do? Let's see. Here's one rule I'll give you. I'm pretty sure it's on tonight's homework. If you put a logarithm in an exponent spot, it sometimes cancels out the exponent if the bases line up. Here's what I mean by that. If I raise 5 to the power of log base 5 of any number, which I'll call x, these two things will actually cancel out, and the answer is x. This becomes useful in transforming functions later in calculus and other places. So if you put a logarithm in the exponent spot, and the base of the logarithm is the same as the base of the exponent, they will cancel out, and you'll just be left with whatever you're taking the logarithm of. Okay? Does that make sense? We'll go a little bit more into why that's true later. All right, let me do an example from the homework before I stop. For now, I want to go on to graphing logarithms. Yeah.
For that problem, do it on your calculator. We do 5 to the log, parentheses 5, parentheses x.
Well, you'd have to have an actual number to do it on your calculator.
What would be the number?
Well, let's put one in. Let's try on your calculator. Let's say we want to know what 5 raised to the log. Well, we can't do log base 5 easily on the calculator, Saul, because it only does 10, so let's make it simple.
Why doesn't it have a log base button?
A log base button?
Yeah.
Honestly, I think it's either a lot of computer memory to put in a table, or it's a lot of calculating power to refig to do the change of base rule itself. It's just not worth it. Plus,